In this video, I will talk about regression variable transformations in Stata. Before you watch this video, please make sure that you have watched my other video called Regression Variable Transformations. So let's go ahead and get started. I have opened up the program here and I have already executed the first few lines of it. So what I will talk today about is regression with quadratic term, regression with interaction term, regression with rescaled variables, and regression with logged rescaled variables. So we would be using two data files, wage 1 and CEO salary 2. So please download them and put them in the directory where they would be stored, and then highlight the code and then just execute the code up here. So let's start with regression model with a quadratic term. So for this, we would be using data on wages, and we would be first running a simple regression model of regression of wage on education. So as we execute and run this, we would see that these are the estimated the results. So here we see the coefficient on education being 0.54, meaning for one additional year of education, wages increase by 54 cents. So now we can predict the wage hat 1, comma x beta is how we get the predicted values. These are the y hats. And then we could graph two-way scatter of wage against education and wage hat 1 against education. So this is the predicted values that we estimated here. So if we highlight and run this command, we would see the graph here. So with a simple regression, this is the estimated regression line here. It's a line. And this is plotting education against wage. So now, is it linear, the relationship between education and wage, or nonlinear? Should we incorporate a quadratic term? So now we can estimate a regression with a quadratic term. So first we're generating education squared, which is education times education, and now we can regress wage on education and education squared. And then we can do the new predicted values. So let's just go ahead and run this part of the code. So here is the estimated regression equation. So here we have the coefficient on education being negative, the coefficient on education square being positive. Both of them are significant. So let's go ahead and plot this time scatter wage against education and wage hat 2 against education. These are the predicted values from this regression. So this is how the graph looks like, and now we have a nonlinear relationship between education and wage because we have a quadratic term. So as we can see here, this including the quadratic term probably better fits all of the observation points. And another thing that we can notice is that at first we have a decreasing effect, and then we have actually an increasing effect. And so how we find actually this minimum point that's happening around here is education star would be equal to minus beta 1 divided by 2 times beta 2. So this is minus the coefficient on education divided by twice the coefficient on education squared. So we can estimate and display this coefficient. So this is basically 6.18. So this means that at an education level of 6.18, we actually have where the marginal effect turns from um, it bottoms out. Okay, so let's calculate the partial or the marginal effect of education on wage. So the way we would calculate it, we basically take the derivative of wage with respect to education. So we would have the coefficient on education plus twice the coefficient on education squared times education. So we can give it several different values of education here. And so we could give it a value of 5, then the turning point that we found, 10 and 15. And we can display all of them. So we have at low value of education, such as 5, each additional year of education brings actually negative lowers the wage by 11 cents. Here, not surprisingly, at the turning point, we see that the marginal effect is 0. And then we have at 10, we have 0.37, and at 15, we have 0.86. So again, we have the strongest effect of education on wage, which is of 86 cents at high levels of education. That's when an additional year of education brings even more in wages. So let's calculate the partial effect of the mean and then the average partial effect. So to calculate the partial effect of the mean, we are first generating using the egen function. We would call it mean underscore education. We would just take the mean of education. And so if we're displaying this value, that would be 12.5 years of education is the average education of the people in the sample. So now we can generate the partial effect of the mean for education, which is again the coefficient plus twice the coefficient on education squared times the mean education. And we would see that this partial effect of the mean is 0.62. So this means for the average person in the sample, we have one additional year of education increases wages by 62 cents. If we calculate the average partial effect, we would take the partial effect for everyone, um, and then we would generate the average partial effect, which is taking the mean of this whole expression that is the partial effect. And if we display it, we would see that's uh, we would see this number here. So again, we have two different methods of calculating, producing almost identical results here. And this is either you take the mean of education first and then plug it into the expression, or you first calculate this expression for everyone and then take the average of it. So moving on, we can repeat the same analysis with experience instead of education. So that would be done a little bit faster. So here we would run a regression of wage on experience, and we can see the graph. It looks like that. So now wage is regressed against experience. This is if we have a simple regression model. If we add a quadratic term, so we have regression of wage on experience and experience square, we calculate the predicted values. So, and then comma x, b calls these predicted values. Then we would graph using graph two-way scatter diagram from wage against experience, and wage had 4 against experience, so this value that we just calculated. So that's what we're going to find here. And we see that again, we find a nonlinear relationship between experience and wage. This time we have actually an increasing marginal effect and then a decreasing marginal effect. So where is this turning point? It seems to be right around here. And the formula for that is that experience star would be equal to minus the beta 1 um, divided by 2 times the beta 2 coefficients. And so if we look at this is the beta 1 coefficient divided by 2 times this coefficient. If we actually calculated, this will be 24.3 years of experience. That's when we would have actually where it's going to switch between positive and negative marginal effect. So let's display the marginal effect of experience on wage at several different values. So again, we're picking up this expression and we will pick at 10, 20 years. We would also estimate it at this number that we calculated here and then at 30. So if we calculate these numbers, we would see that at 10 years of experience, then the effect of experience on wage is 17 cents. At 20 years is 5 cents. Then it goes down to zero at 24.3 years, and then at 30 years, it actually turns negative. So in the beginning of your career, at say 10 years of experience, each additional year of experience brings you about 17 cents in wages. That's until about 24 years, where each additional year of experience brings no additional wages. And then after, at 30 years, each additional year of experience actually brings 7 cents lower wages. So to calculate the partial effect of the mean and the average partial effect, first of all, to calculate the partial effect of the mean, we would calculate the mean of experience. So we do that by egen. I will call it mean underscore experience. We take the mean of the experience variable and then displaying this that we just calculated. So that would be 17 years. So the average experience of people in the sample is 17 years. And then we can generate the um, partial effect of the mean for experience, which is the coefficient plus twice the coefficient of the squared term times the mean experience. And then we have this being 0.9. So for the average person, each additional year of experience brings about 9 more cents in wage. To calculate the average partial effect, we would simply generate this value for everyone in the sample. So for each observations, depending on their experience, we would get the partial effect. And then we would simply take the average of these partial effects to get to the average partial effect for experience. And then we see this is actually the number for the average partial effect. Okay, so moving on, let's talk now about interactions, interaction terms and regression with them. So to do that, let's first run a regression, basic regression of wage on education, experience, and tenure. Get the predicted values using predict, giving it the name wage hat 5, comma xp. These are going to be the fitted values or the predicted values. And then graph two-way scatter wage against education and this predicted value against education. So let's see what happens here. So these are the coefficients. We have positive and significant coefficients for education, experience, and tenure. Experience is only significant at the 10%, not at the 5% significance level. So if we plot the data as well as the predicted values, one thing that is happening here is that for each value of education, we have several different values of experience. That's why we don't have a line here, because it's not a simple regression. We just have several values of experience. And so that's why we see um, several predicted values. That would be depending on what the experience is. So now let's go ahead and generate an interaction term, two interaction terms. So if we generate education times experience, and then experience times tenure, and then we can run a regression with the first interaction terms, a term of education times experience, then predict the fitted values, comma xb, and then graph these wage against education and this predicted value against education. So first of all, let's run this and see. Now we have the same regression, although now we have education times experience being our independent variable as well. So if we look at this coefficient, actually, we do not see that this coefficient is significant. So basically, education and experience, the interaction of them does not have any significant effect on wages. So again, we would see the same thing where wage depends on education, but that depends on experience. So that's why we have multiple predictions for wage. Okay, so now we can calculate the partial effect of education on wage at several levels of experience. So notice that if we want to calculate the partial effect now, we have to calculate at several levels of experience. So the partial effect is the coefficient on education plus beta, the coefficient on experience, times whatever that experience is. And so here we would just pick 10, 17, which was the mean, and then 30. So let's see. Um, let's see these. So here we have um, for the level of experience of 10 years of experience, we have an effect of 70 cents of education on wage. At 17 years, we have 79 cents, and at 30 years, we have 95 cents. So this is how much each additional year of education affects wage at these different levels of experience. So we can also run this regression with um, experience times tenure. And now we see that actually that coefficient is negative and significant. So we have positive effect of experience on wage, positive effect of tenure on wage. So there's individual effects increase wages, where if we multiply them together, they have a negative effect. So this means they kind of cancel each other out. There's no boosting of effects or magnifying of the individual effects. They actually do cancel each other out. So now let's talk about regression with rescaled variables. And so here we would be using the CEO salary example, using this data file. And so I would use the data and then keep salary, sales, profits, and then log of salary and log of sales. I will describe and summarize the data. So here what we see is that this is data for the salaries of CEOs. And so this is measured in thousands of dollars. And sales, this is the sales of the company, are measured in millions of dollars. And then profits are measured in millions as well. And then we have the log of salary and the log of sales. So here's the data that is being summarized here. So we see the mean values for each of the variables. So note here that as we rescale the variables, that there are two effects in place. So if we rescale salary from thousands of dollars into dollars, what we need to do is just generate a variable. I will call it salary underscore D for dollars equals salary times 1,000. And if we rescale sales from millions of dollars to thousands of dollars, we need to multiply the sales times 1,000 to get the sales in K in thousands. So if we run now the descriptive statistics and we summarize these variables as well, what we're going to find here is that this is the original variable and this is the rescaled variable. And so if we compare the two values, they're actually identical the same because all we did is we just shifted the decimal point 3 places because we multiplied by 1,000. So likewise, when we moved sales from millions to thousands, we multiplied this number by 1,000. So we basically just moved the decimal point 3 times. So which ones you choose to use of the rescaled variables, either the original or the rescaled one, is a matter of preference. And typically there's no loss in information unless we decide to round. Like if we round this to 865, whereas this we keep it like that, then of course there'll be loss of information. But that's about rounding, not about the rescaling of the variable. So now let's go ahead and estimate different regressions. So here we would have regressions with the original then rescaled variables. So here we have regression of salary, sales, and profits. So these are the coefficients that we obtain. So now if we rescale the dependent variable, so notice that this one was in thousands of dollars, now it's in dollars. So basically this one we multiply by 1,000 to get to this one. So here are the coefficients. So if you compare these coefficients with these coefficients, you will see that all of the coefficients got multiplied by 1,000. So when you rescale the dependent variable, you multiply by 1,000. All of the coefficients get multiplied by 1,000. So now let's see what happens when we actually um, transform the independent variable from millions of dollars to thousands of dollars. So this one is also multiplied by 1,000. So if we actually compare, we again have the original salary. This is the transform variable, and these are the same variables. If we compare these results right here with salary the same, so our dependent variable is the same, and the independent variable changed by multiplying it by 1,000, what you can see is that the coefficient here got divided by 1,000. So this one, this coefficient got divided by 1,000. And notice that the rest of the coefficients right here are still the same. So if you transform an independent variable from uh, by multiplying it by 1,000, then the coefficient would be divided by 1,000. And so the final regression that we have here is where we have both the dependent and independent variable transformed. And in this case, we see that these are the coefficients that we see here. And so comparing, let's see, if we compare this to this, so here we have the same independent variables, only the dependent variable got transformed. You see that this coefficients here are multiplied by 1,000 to get to these coefficients here. So again, that's the effect of what happens to the dependent variable. What happens to the independent variable is if you compare this regression here, where sales, this is the original coefficient here, and now if the sales is transformed by multiplying it by 1,000, you see that the coefficient got divided by 1,000 and the rest of the coefficients are the same. So all of these regression outputs are fine, but sometimes we want to present the results in the best possible way. And so I would suggest that actually this coefficient is very, very, very small. So of all the regressions, I would probably not pick this regression because of this very small coefficient. I would pick any of the other regressions. And this one has all of the coefficients are above um, 1. So that's actually an easy to read table. So perhaps pick that one. So the point here is that when we have rescaling of the variables, then the coefficients would be rescaled as well. So now let's look what happens when we actually have regression with logged rescaled variables. So I'm going to execute this code. So here we have regressions with log transformation. So here we have the level regression in levels. So here we have salary regressed against sales and profits. These are the coefficients. Then we have the log level regression, and then we have the level log and the log log. If we notice actually what happens with the R squared and the adjusted R square, we would actually see that the last regression right here would have the highest R square. So meaning the last regression here has the best fit of them all. And in this particular case, it happened to be the log-log regression. It doesn't have to be, but it so happened to be the log-log regression. So based on this, we will actually use the log-log regression for the later analysis. Okay, so now let's rescale salary from thousands of dollars into dollars and then take the log of it. So we already calculated this variable, taking the log. This will be the log of salary in dollars. And then rescale the sales from millions of dollars to thousands of dollars. So again, that variable was transformed. We're taking the log of it. So if we now take descriptive statistics with the log of salary and the log of salary that was measured in dollars, so in the log of sales and the one that was measured in dollars. So all of these results are now of the logged variables, and they all are of reasonable magnitude, so they're all acceptable. So let's do a regression with the original log variables and the rescaled log variables. So here what we have is the regression of log salary on log sales and profits. So notice what happens to the coefficients. So we obtain these coefficients here, which is 0.19. If we transform the dependent variable by multiplying it by 1,000, keep the same independent variable, notice what happens to the coefficients. Basically, nothing happens to this coefficient, nothing happens to this coefficient. Only the constant changes, the intercept here. Now, if we keep the original dependent variable, but we rescale the independent variable, uh, what happens? Well, again, nothing happens. The coefficient is the same, only the constant changes. And finally, if we transform both of the dependent and independent variable, we see again same coefficients, slope coefficients, but different constant. So the conclusion here is when logged variables are rescaled, the coefficients actually do not change. So this concludes the Stata program for different transformations in the regression variables.